But my name is Elad Hazan. I'm a professor here in Princeton, and I run the local Google lab. And this is the last talk of today. Thank you for bearing with us. I'll try to keep it as short as I can. I'm also super tired. So yeah, I'll try to keep it less than 30 minutes. I'll be talking about non-stochastic control. The title of this talk is tribute to one of my favorite papers of all times, the non-stochastic multi-arm bandit, which is by various authors, including Rob Shapiri, who's supposed to be here somewhere. At least I saw him before. And this is joint work with a lot of collaborators in the past 2 years. Mostly I'll talk about work with Naman Agarwal, Karan Singh, and Sham Kakade. And various of my students have given talks today and tomorrow about other works. So I'll talk about some new controllers or algorithms for control. They have been implemented, and the code appears on open source on GitHub, so you can feel free to go there and try it out. We have tried it out, and I hope it can come in useful. But this was written, I should say, this was written mostly by undergrads, John, Paula, and Alex. So the setting which I'll talk about, and I'll talk only about kind of the simplest setting, linear dynamical systems and controlling them. And thankfully, Russ and many others have talked about how important it is, so I don't have to convince you. And in this setting, we have some input U and some output Y, which is an observation of the state X. And the way that this Y is generated is by projecting the state, which continues to be manipulated linearly according to a linear transformation of the previous state, previous time, some control U and some perturbation W. So this is kind of the special case I'll talk about. More generally, you can think about other nonlinear dynamics, and we have kind of thinking about that too. But maybe because we're short on time, I'll only talk about the linear case. And there are two problems you can think about. The first is prediction. So given all these U's, maybe we want to predict the next and the previous Y's. We want to predict the next Y. And the other is control. The more challenging one is we want to compute these U's that you put into the system. They will minimize some cost function or aggregate cost function. By the way, feel free to interrupt me at any time. Yeah, so what's changed since the 50s? This is, by the way, Rudolf Kalman receiving a Medal of Freedom from President Obama on the work on Kalman filter, which we all know. And yeah, I love this quote. So this is a reviewer that gave us a comment. So as opposed to deep learning, control got us to the moon. Pretty funny. I'm from the machine learning community, so I found this funny at the time. But I guess, there is truth in that. It's a very deep mathematical subject. But things have changed since the 60s. So now we have controllers that are based on deep neural networks. Even without recurrency, we know we know very little rigorous statements about them. So I'd love to say something rigorous about it. We have misspecified systems, adversarial, non-Gaussian noise. Russ kind of talked a lot about why this is important in applications. And high-dimensional data that require efficient methods. By efficient, I mean coming from the optimization community, SOS is not efficient. Maybe it's efficient for low-dimensional, but not once you go to hundreds or thousands of variables, which we might want to apply to. So I'll talk about non-stochastic control. We have done some other work about boosting, which is a way sort of to handle nonlinear dynamical system. It's kind of the only rigorous thing I can say about these. And they also relate to work by Rob, which I alluded to before. Yeah, so I'll talk mostly about the first problem, non-stochastic control. And without ado, let me introduce it. So this is work with Naman, Brian, Sham, and Karan, and appeared a year and a half ago. Oh, John Langford just came. Hi. So let me define the problem. We have this linear dynamics, and I'm now assuming that we can see the state, x. So we have this x at time t plus 1 is a linear manipulation of x at time t, and whatever we put it, u at time t and w, and then we get some cost. We pay some cost, and we'd like to minimize the cost. I'm going to assume that this w, this is the main deviation from classical control. I'm not going to assume that it's an IID Gaussian or any kind of randomness about it at all. Okay? So this can be completely adversarial. All I want to assume about it is that it's bounded by 1. Let's say. It can be bounded by anything, but let's say the bound is 1. And so what kind of approaches have been applied to the setting? LQR, that's probably the most common and the most applicable kind of primitive in control. And that if we know the system A and B, we can compute, I wrote it here. We can compute the optimal controller, closed loop controller. So this means that we can compute a matrix K that if we play U, which is K times X, this is the best thing you can do. Okay, if you have Gaussian IID nodes. And this is provable, and it's a beautiful theory, and also works pretty well. But again, I want to deviate from this setting. Then there is something called age infinity control. So age infinity control is the way of the classical way in control to deal with worst case noise. And the way it's dealt with is by solving a min-max formulation. So trying to find the best controller for the maximum kind of worst case noise that can ever appear in the future. So it took me a long time to kind of find the correct word for it, but the correct word seems to be pessimistic. So this is a pessimistic way of doing control because we plan for the worst case, but maybe something not worst case is going to happen. And then too bad, right? We could have done maybe something better instead of planning for the absolute worst case. So what are we missing? What we'd like to do is one thing I kind of didn't say. I'd like to solve general loss functions. So this CT that I had in the previous slide, I'd like to be general convex loss functions like we have in machine learning and not quadratic. So this LQR kind of solution applies to quadratic losses and also for age infinity control even more so if you want an efficient algorithm. If you have, let's say, a hinge loss, you have run into computational issues with these two approaches. And what I will present will actually be okay for any convex loss function, even if it's adversarially chosen. So I want a computational efficient method, and I like an optimistic metric, which allows, so more optimistic than this, which will allow me to handle adversarial noise. So here's the model we work over, online control. So iteratively we select some input, and then we observe the state, and we incur loss. So we don't compute anything kind of in advance forever. And the goal is regret, or more precisely, policy regret. So what I'd like to do is choose a sequence of controllers. I'm in the closed loop setting, so I'm allowed to see the feedback. Took me forever to understand what closed loop means. It's basically what in online learning we always do. So we can see the feedback, kind of modify your decision, and play something else. It's not like you decide everything in advance. Yeah, Chaba.
You don't see the state before you select it?
You can, yeah. You see the current state, and then you...
Okay.
Yeah. Oh, you're right. Yeah, typo. Sorry. Yeah. Actually, what I will describe, you don't even need to that. You will not need it. But let's say that you do. So it's even stronger. Okay, so... right, so we want to minimize regret, and this is policy regret. So this means that we want to choose over all possible noise that can appear. We want to minimize the sum of cost for the control that we choose. Minimize the difference to the best thing we could have done. Now, best thing we could have done is too strong because anything could have happened. So I only compare to a certain set of policies. Okay, so the set of policies that makes sense maybe is a set of linear policies that we know that are optimal for LQR. So we compare maybe to a set of linear policies. We can generalize this, more and more and more. So with more recent work with Max and others, we can look at much more general things, even changing policies and so on. But for now, let's assume I want to compare to a linear policies. And then what's written here is the state xt hat. It's not the state that I saw. It's the state that would have happened if I had played this policy from the beginning of time. That's kind of the correct metric to compete against. So this is what I said. And this is kind of supremum over all possible noise. Okay, so the setting is clear? Okay, so the main result I want to talk about is this algorithm. So there is a sufficient algorithm that can minimize regret in this setting, and it competes with all possible linear policies that are interesting, that are stable. And it achieves a regret which is bounded by square root number of iterations. So this means that on the average, your loss is going to be as small as the best thing you could have done in hindsight, even without knowing the, right, so kind of, so we don't know the perturbations in advance. These perturbations are adversarial, you don't know the cost in advance, and you can still do it. Yeah, so this is the main result, and any questions so far? I should remark, so in the case that the noises are Gaussian, ID Gaussian, this recovers LQR. So you do as good as the had you planned using the Riccati equation and so on. Okay, but
you're searching over a fixed policy.
Yes.
With the linear policy?
I'm not, no. So kind of computing, I mean, competing with this might be actually even hard, like for general cost functions. So I'm going to do something else, but I will have this guarantee. So I plan a different kind of control, but I compete with this policy class. So this is called in learning improper learning. So you do something, but you compete with something else. Okay, any other questions? Good, so let me tell you what we do, and for that, they're kind of, I'm not going to prove anything, but kind of tell you how this thing is derived. And there are three kind of not very complicated steps. The first is to relax, convex relaxation. So if we were to write the control in terms of k, I have some k, the best k in the world, someone told me what it is, and I want to write a control in terms of this k. How does it look like? I can open up the recursion of the linear dynamics, and I will get this expression as a function of k. This is an expression that depends on the previous noise terms. Okay, and it depends, so these are fixed by nature. Nature chose them adversarially, but it depends polynomially, and I should say pretty bad maybe, on the matrix k. Okay, so this is not a convex function. There's no reason for this to be a convex function of k. It's a polynomial. Okay, so this is a hard maybe thing to optimize over. That's why I want to deviate from the k. On the other hand, I could replace these matrices here by some other set of matrices and call them mi, and kind of just forget the whole structure and say maybe I will play a control which is a linear function of the previous perturbation. So that is, we call this the gradient perturbation controller because it plays over the perturbations, and it will do a gradient method over them. Okay? This is reminiscent of something called Euler reparametrization, for those of you who have studied control, related to many things in control, but never applied in a kind of a setting. Okay, so now if I do this reparametrization, my cost functions that are convex functions in the state and the control and the control are going to be linear in M, so convex function of linear is also convex, so this whole thing is convex. So at least I can compute now the best matrices in hindsight. That's already good, right? So from something that is hard to compute, I moved to something that is easy to compute. Furthermore, I can add constraints, safety, whatever you want. It's fine. As long as there are convex constraints, you can at least you can optimize it. So that's already a good thing. Number two, I don't like the fact that here we have to sum up to the beginning of history with the perturbations, because that's too many parameters, right? We have too many parameters in our, and those of you who know statistical learning theory, you cannot have the number of parameters grow with number of examples, right? You will not get any generalization. In this case, you will not get any meaningful result. So what we can do, we choose a different kind of, we don't go all the way back. We only take a few matrices. How many we can quantify that? So the way to do it is to say I take some stabilizing controller. This is not the optimal controller. I take a stabilizing controller K that can be computed from the system A and B a priori. This is not the optimal thing, and it's not optimal to the noise, not optimal at all. But at least it prevents from exploding. That's the goal of this. And to this, I'm going to add a finite sum of matrices that are not too many. So how many do we need? We can prove that with log many such matrices, you can actually express the optimal controller in hindsight. So this is a representation kind of statement. And furthermore, we can say that no matter what, if these are M are bounded, this will never explode. The system will never explode using this kind of control. Okay, so this is already a nice setup. And finally, the last thing, the last component is that we cannot know. So the whole problem is an online problem. I cannot know in advance what these M's, the optimal M's, are going to be because I don't know the perturbations in advance. These are adversarially chosen. So we have to learn them. Okay? So this is a learned controller. And how do we learn it? We will learn it by some gradient method. Nevertheless, when we play a set of matrices, the state of the system changes. And then I play a different state matrices, then it changes again. So I have some issue here that whatever I play, it's going to affect the loss function of the next iteration. And this is a setting called online learning with memory. And luckily, many years ago with Shai and Oren, we looked at this setting and we have some way of kind of solving it in a good way, of kind of characterizing what kind of methods will still give you regret, even though you're changing your decision and your loss functions change as a function of what you did in the past. So this is the last component. But when you put them all, yeah, question, Emma.
Clarification question. Do you know what T is in advance so you know how to specify H, or are you actually creating new matrices over time?
Oh, okay, great question, yeah. So the reason Emma asked this, because this H I wrote here, it needs to be log T to kind of get the optimal thing. And there are several answers to this. So first of all, yes, let's assume we know T in advance, that's already easy. If you don't do, what do you do? Some classical learning, we kind of double. Now, because this dependence is logarithmic, it's really, you have to double it very often, so it's really not a big deal. Finally, this is a theoretical bound. So in practice, take H equal 10, it works wonderful. You don't need more than that. Okay. So this is the method. The method says the following. You initialize the matrices to be 0, let's say, and then you iteratively observe the perturbation. So you don't observe it directly. You observe the state. You know the control that you put in. You know the state. You can subtract all of it, get the perturbation. Once you have the perturbation, you can create a loss function as a function of the matrices that you played. And that's just a convex over linear function. And you update your M using gradient descent, all-line gradient descent. So that's the whole algorithm. Again, it's a different kind of algorithm than LQR because this is a learning algorithm. It adapts to the sequence of noises that it sees on the fly. It doesn't compute everything in advance, and it gets the aforementioned regret guarantee. Let's see how. Okay, I promised to be early, and I think I will deliver on it. Okay, so yeah, so that's the algorithm. Any questions about the algorithm or the guarantee? So it turns out that kind of a similar technique can yield improvements even to classical problems in control, such as tracking. So in tracking, it's a very similar setting, but your loss functions are more special. They are quadratic. And because they're quadratic, they have a property called strong convexity, which is a useful property, and we know in online learning that we can get fast rates for this kind of setting, and therefore we can attain a regret which behaves logarithmic in time as opposed to square root, and this even improves classical Kalman tracking, right, from the 60s. So in the same setting. Now this assumes that you have a Gaussian IID noise, because that's the only way we know how to prove that the strong convexity holds in the reparametrized form. We need it to hold in the reparametrized form, not in this state form. So hopefully Karan will speak more about it tomorrow. I will just remark, we have some more, what if we don't know the system? So we have more works that kind of deal with it, how to identify the system with Sham and Karan, and with Max and Karan. We can even deal with kind of partially observed state and get kind of tight rates even for LQR. So kind of even the partially observed LQR, you don't know the system, you don't know anything, you can still compete with it in adversarial noise, which I think is pretty neat, and kind of by a new method. Okay, so it's a different method than LQR. Okay, I think I do have time. Okay, I'll say a few words about boosting. So, yeah, what do I do if I have nonlinear dynamics and someone gives me a neural net to play with? So in this regime, we don't have anything we can say, at least rigorously, even in the supervised learning setting. It's hard to say things. So definitely not in the recurrent setting, but I'd still like to say something formal about how to improve recurrent neural networks, LSTMs, and so on that have become very useful for controls. So the setting is the same dynamical kind of system setting. I want to choose the control to minimize the cost. Disturbance is added. Again, it can be stochastic or adversarial. I want to minimize the same thing, policy regret, compared to a class of policies. And this depends on all the choices I've made in the past. So everything so far the same. But those of you who are familiar with boosting know that the classical setting does not have memory. So maybe we have weak learners that we can combine them together and create a strong learner in a statistical supervised learning setting. We've been doing a lot of work into this. There's been a lot of work extending it to various settings online and so on. But in control, we have state. So when we have state, it's not at all clear how to combine these different controllers, and each of them thinks that the state of the world is different, into one coherent controller that can do something and with respect to its own state. It's not clear immediately how to do it, okay, because of the memory. So here there is, so step one, we can kind of alleviate the issue of state by looking at stable systems that allow for finite memory, and therefore reduce to a memory-less, but maybe very long memory-less kind of situation. And second thing we can do, we need a notion of weak learner that is a notion of boosting that's even different. What does it even mean to do boosting in this kind of setting? And so the guarantee that we are shooting for is different. So if we have a weak learner that can generate a sequence of controls that minimize the loss with respect to a class of policies, this is kind of our assumption. We have some kind of weak controller. The goal is to combine them in such a way we cannot improve the regret. Regret is going to be, that's what we had, that's what we're going to live with. But we can compete with a larger class of controllers. That's going to be our goal. So if we have some neural net, or we have some machine that can compete with all controllers that are LSTMs depth 1, then we can boost it to compete with all linear combinations of that class. And that can increase the power of the set that we compete against. So this is the type of result we are shooting for. I'm going to skip the technical details and allow Natalie to talk about this tomorrow. But I will conclude with a few kind of illustrations of where these techniques are useful. Unless there are any questions, I'm happy to take now about things I discussed. Okay, so I will show you a bit of demonstrations where these things are. Okay, we don't have anything close to that. Maybe Russ does. So yeah, we just kind of played around with these things. So the first thing we played around with is a linear dynamical system with noise, just standard Gaussian noise, and kind of see that sanity check that these techniques are reasonable. And here LQR is the kind of the purple line. Here is the absolute best. You can never improve upon it. And indeed we don't. But at least this is the weak learner I described in the weak learner here is taken to be this gradient perturbation controller, and it improves by boosting to something much better. That's at least a good sign. But if we change the noise to see something different, let's say that the noise is now random walk or sine, then all of a sudden you can see significant improvement compared to both LQR and to age infinity control. So it kind of improves. Age infinity control is not even here. It's really a disaster. But LQR is here. It's the purple line. For example, for sine noise, it's the worst. And our weak learner is better. And then an RNN is better. And if you boost them, you get even better. So as you would expect by the theory. We have some kind of preliminary experiments with not robots playing soccer, but something a bit kind of along the way. So pendulums or some kind of controlling of systems, trying to keep this bar here straight. And kind of an LQR-based planner has exploding loss. This is a nonlinear system, by the way. But this gradient perturbation controller can do much better. And if you boost it, you do even better. So that's pretty much what I wanted to say about robust control. And I'm kind of advocating for the statement that if you really want robust control, you have to move to the non-stochastic setting. and talk about regret as opposed to competitive ratio, such as edge affinity control. What can we do with deep nets? We have some approach to kind of combine them in a meaningful way with vigorous guarantees. And I guess Cyril talked today about exploration basis for control. Please look at this website for more information. And thank you for your attention.